Hello student, to the course for Foundation of the Classical Electrodynamics. Today we have module 4 and lecture 67, and in this lecture we will discuss about the Lorentz gauge and then we will going to discuss Maxwell's wave equation. So, we have class number 67. Okay, so far whatever we have, let me quickly remind that there are 4 Maxwell's equation and we wrote this Maxwell's equation as homogeneous and inhomogeneous form. So, that was the first equation having the source term. So, this has to be a non-homogeneous equation. Second equation, which is divergence of B, that is 0. Third equation, curl of E plus del B del T, that was 0. And fourth equation is curl of B minus mu 0 epsilon 0 del E del T, that is mu 0 J R T. So, these 4 equations, among these 4 equations, these 2 were homogeneous, and from this homogeneous equation we find the relationship like E is equal to minus of phi minus of del A del T. So, I can extract the information, this information in terms of a scalar and vector potential, just exploiting these 2 homogeneous equation, and B was curl of A. And after that we put this information in 1 and 4, and putting this, say, let me write down this equation, say let us write it as 5 and 6, and putting equation 5 and 6 in equation 1 and 4, which are non-homogeneous in nature, we get these 2 equations, the following 2. We get grad square phi plus del A del T, and then divergence of A is equal to minus of rho function of R and T divided by epsilon naught, and another equation is divergence, gradient of divergence of A, then plus 1 by c square d phi dt bracket close minus of Laplacian of A minus 1 by c square del 2 A del T square, that is equal to mu naught J R T. So, after that what we have? We had the Coulomb gauge. and the condition of the Coulomb gauge is divergence of A has to be 0, that is the constant we are using. After using the Coulomb gauge, what we get? We get the first equation as this quantity is 0, we get the first equation as this. So, that means phi is now satisfying a simpler Poisson equation, and the next equation which is not that simple. So, we had grad square A minus 1 by c square d2 A dt square, that quantity is equal to minus of mu naught j. This source has to be given because this is a known quantity, without that we can't calculate the magnetic or electric field. And then we had a term like plus 1 by c square and then del t and then gradient of phi. So, whatever the phi we have here, the solution after doing the Poisson equation, I plug it here, so that the right hand side is known and you can calculate this also. So, from then we can calculate A, which should be a function of r and t. So, this equation gives me the solution of phi, that phi I put here, and then I should have the equation, a wave equation with a source term, and that wave equation I solve with a source term to get my A. So, that is the recipe when we use the Coulomb gauge. Now, in today's class we are going to discuss the Lorentz gauge. So, what is the advantage of the Lorentz gauge? Let us check. Lorentz gauge. So, in Lorentz gauge, what we do, we make in Lorentz gauge, what we make is this. Instead of taking divergence of A equal to 0, we take divergence of A equal to minus of 1 by c square del phi del t. We just take it. Why we take this? Because if you look carefully, we have a disturbing term here. So, if this term is not there, I am making a line here. So, I have a term here. If this term is somehow 0, then my second equation will be much simpler. So, in Lorentz gauge, what we do, we just take A in such a way that A and phi in such a way, because we have a liberty to A and phi, that this condition should satisfy. If that is the case, then what we are getting out of that? Then these two equation, whatever the equation I wrote here. So, maybe I can put a name here. So, maybe this is 5, 6 is there. So, 7, 8. These are my fundamental equations, and now I am putting the gauge to simplify it. So, with this condition, equation 7 and 8 become much simpler, and that is this. So, we have say equation 9 now. After putting this condition to equation 7, what we get? We get this divergence of phi, then we have plus del t, we have divergence of A. In place of divergence of A, I should write at minus of 1 by c square d phi dt, that I wrote simply. Rest of the term is simply minus of rho epsilon naught r t. Now, you can see that this is having a very well known form, and this well known form is divergence of phi minus 1 by c square d 2 phi d t square. This is nothing but the wave equation with a source term minus of rho epsilon 0 r t. Let us put equation 9, this one. So, this is the equation we are getting after exploiting the Coulomb gauge, and now I will do the same thing for other, and for other equation it is straightforward because this term will completely 0, and we have equation 10 which is for magnetic which is for the vector potential A, and the equation is again something like A minus of 1 by c square d 2 A t square is equal to minus of mu 0 j function of r and t. So, both the equation are satisfying. So, now both the equation, which equation? Equation 9 and equation 10 that is equation for both the equation for phi and A, in other word, because in equation 9 we have only phi, in equation 10 we only have A, satisfy the wave equation. With a source term. And we have the method to solve the wave equation with a source term. Okay. Now, like the before, so this condition, this Lorentz gauge condition, I need to fix it because I considered that gradient of divergence of A minus 1 by c square del phi del t, but for given A and phi this condition may not be true, right, this condition may not satisfy. So, then what we do? We need to fix that like we did in the Coulomb gauge. So, now suppose for a given phi and A, because this is given, and for that there is a possibility that this is not satisfied, that is divergence of A plus 1 by c square del phi del t. Okay, maybe I am making a mistake here. Yeah, no, it's okay, fine, there is a negative sign. So, this quantity may not be equal to 0, right. That means, given phi and A does not satisfy the Coulomb gauge, but we can make them satisfy with the proper choice of A and phi, that the liberty that we have. So, that we are going to exploit. So, if that is the case, if it is not equal to 0, then let this, if it is not 0, it should have some value. So, let me write this value. So, suppose this is not equal to 0, and that is why I can write that this is not equal to 0. So, it should be equal to something, and this something is say g, which is a function of r and t. It has to be a scalar quantity because left hand side is a scalar divergence, and this is scalar quantity. So, right hand side should be a scalar field. Now, the aim is to, our aim is to find a prime and phi prime such that A prime and phi prime such that these condition satisfied, the Lorentz gauge condition satisfied. So, this is nothing but the condition of the Lorentz gauge. So, our aim is to find out a set of A prime and phi prime such that this condition satisfied. So, how to do that? Let us check. So, that is our aim. Now, we know that A prime can always be written like given A plus the gauge function, this psi chi is our gauge function, and phi prime I can write as phi minus del chi del t. Chi should be a function of r and t. This is r and t, and we just need to fix this function. We need to know what function this is. If I put a suitable function, then I can have my A prime and phi prime such that it follows the Lorentz gauge. It satisfies the Lorentz gauge, and my equation becomes simpler. Now, next is, if I make a divergence here of A prime, right hand side it should be divergence of A plus the Laplacian of this function, and left hand side what we do, I multiplied 1 by c square and make a time derivative with respect to make a time derivative of phi prime, and right hand side it is simply 1 by c square d phi dt minus 1 by c square d2 chi, which is a function of r and t, this. Now, I simply add both the side because left hand side I want something. So, if I add, then the left hand side becomes divergence of A prime plus 1 by c square d dt, that, and this term is divergence of A plus 1 by c square del phi del t, this quantity, plus I have r t minus 1 by c square d2 chi r t dt. Now, we make this quantity equal to 0. So, that means, so this has to be 0 because this is our, so we want this to be 0, right. So, this quantity has to be 0, equal to 0, and what value we have here, this is the given value, this is not equal to 0, and this value is, suppose I mention here, this is equal to something called g. So, I now have this value as g. So, if that is the case, then I can have the equation, and that equation simply tells me that gradient Laplacian of this scalar field chi minus 1 by c square d2 chi t, that is equal to minus of g RT. So, that means if I choose my chi in such a way that satisfies this equation, which is again a wave equation having a source term, then eventually I can form my A prime and phi prime exploiting this expression such that it satisfies the Coulomb gauge condition. So, step by step I derive everything. So, this basically tells us that if I put certain constraint, certain gauge like Coulomb gauge or Lorentz gauge, then my equation becomes simpler. So, at the end of the day, what equation we are getting here? We are getting equation 9 and 10 to solve, and once you solve, because rho and j is given, if rho and j is given, we can solve equation 9 and 10 and we can get phi and A. As soon as we get phi and A, we know what is the value of electric field and magnetic field, because they have a relation. Now, how I get equation 9 and 10? Exploiting the Coulomb gauge. And how I exploit the Coulomb gauge? If the condition divergence of A plus 1 by c square del phi del t is not equal to 0, suppose it is a G, then I exploit the relation A prime and phi prime, considering the fact that A prime phi prime will produce the same E and B. So, since A prime or phi prime are producing same electric field and same magnetic field, instead of using A and phi, now I am going to use my new A prime and phi prime. This new A prime and phi prime can be constructed from the given A and phi and also an arbitrary function chi, which I can fix, which I can put, it is my choice. Now, I choose my chi in such a way that it satisfy the Lorentz gauge condition to make the solution, make the equation very simple, and we find that the chi I choose in such a way that it satisfy this equation. This is again a wave equation with source term. So, we need to solve this equation to find my chi. So, this is my hand. So, what chi I will fix. So, basically we need to solve this. This is a wave equation with a source term. And this source term is again given, because when A and phi is given, then I can find that the divergence of A plus 1 by c square del phi del t, that basically G. So, I know that this is not equal to 0, that is the initial condition. So, that initial condition I am going to exploit here to find out my chi. So, okay, so this is roughly the discussion of the Coulomb gauge, a just primitive discussion, so that you can have an idea what is the meaning of Coulomb gauge, what is the meaning of Lorentz gauge. So, okay, this is Lorentz gauge, by the way. So, then you understand that how exploiting the Coulomb and Lorentz gauge, you can simplify the equation in terms of the vector potential and scalar potential, and then you use this vector potential and scalar potential to find out your final equation. So, the Maxwell's 4 equation, which deal with the value of electric field and magnetic field, the information is gradually, we extracted this information from in the form of A and phi, and eventually we solve this A and phi. So, now after that we will do a very important thing, and that is called the Maxwell's wave equation. So, now we had an idea about the wave equation, because wave equation we had a special separate lecture. So, we will going to find out how the Maxwell's 4 equation leads to the wave equation. So, let me write down here first. So, the next topic is Maxwell's wave equation. Say in free space, let us start with a in free space. Okay. So, in free space means eventually without any source term. That means rho is equal to 0 and j is also equal to 0. So, if I write down the Maxwell's equation under this condition, the equation become very simple, and this will be the form: divergence of E should be equal to 0, divergence of B will be equal to 0, curl of E will be minus of del B del T. This is perhaps the simplest form of the Maxwell's equation without any source term, and curl of B is equal to mu 0 epsilon 0 del E del T. So, in principle they are all the 4 equations are homogeneous equations. Now, we will going to exploit this equation. So, this is equation 1, this is equation 2, this is equation 3 and 4. So, from equation 3 we can have, so what do we do from equation 3 is we take the curl of both sides. Okay. So far we are dealing with the divergence of both sides and check that the left hand side and right hand side is consistent or not. But now what we do that we take the curl on both the side. So, if I do that, curl of E is equal to minus of del T, then curl of B. Okay. Now, curl of E again is a very, this is the famous identity, that is minus grad square E plus gradient of divergence of E. This identity we use several times, so you should remember this identity. Then minus of del T, and in the right hand side we have curl of B, and curl of B in exploiting the equation 4, I can simply write it is mu 0 epsilon 0 then del E del T. Okay. Now, this quantity in free space, this quantity is 0. This quantity is 0 because there is no source term in the free space and divergence of E should be 0. If we make this term equal to 0, the rest of the term is like minus of divergence of E is equal to minus of mu 0 epsilon 0 and then del 2 E del t square. So, I can make it plus both the side. So, this exactly looks this equation exactly is like a wave equation. So, let me write down the wave equation this side. So, the general wave equation was grad square psi as a function of r and t is equal to 1 divided by velocity square 1 by v square, and then d2 psi function of r and t dt square. That was the equation, wave equation we discussed earlier, where v was the velocity. So, now if I look carefully these two equations, then we can see that E is also following. So, let us remove this from both the side. So, E is basically satisfying the wave equation under the condition that this can be written in terms of the velocity. So, how I write this in the terms of velocity? So, I can simply write E minus 1 by c square d2 E dt square is equal to 0 when c is nothing but 1 by root over of mu 0 epsilon 0. So, during the calculation, when Maxwells did this calculation, he find that mu 0 epsilon 0 is sitting in the place of 1 by c square, and he calculated mu 0 epsilon 0, and he find that this value is very close to the velocity of light c, and then realize that light is nothing but an electromagnetic wave. That was the revolutionary findings. So, here we are doing the same thing. Now, if you do the same thing for B, like this is a homework. So, please try to do the same thing for B. I exploit equation 3 by taking a curl of E, and you can do the same thing by taking the curl of. So, try to do this, and you will find that you will going to get the same result for B as well with the same velocity. So, if you do what we get, so using equation 4, and you will get the similar expression like you get for E. Okay, that is a homework for you. You just check it. Now, let us consider that what should be the solution. What should be the solution that we are going to consider quickly. So, it is called the plane wave solution. Plane wave, very special kind of solution, because we know that the wave equation has a specific kind of solution. So, let me write down here also. So, when we have this equation and we mention that the solution should have a specific form, and the specific form, if I write, it should be like psi 0 and say e to the power of I. So, something like k vector and k dot say r minus like v t. Okay, it is like a z minus v t kind of form. So, one should expect this kind of form for plus minus. This is the general form, because the general solution, if you remember, it should be This is a plane wave solution, but the general solution in one dimension, if you remember, it was z plus minus v t. That was the form of the solution of the wave equation when g was the function. So, in one dimension, that was the equation, and we find that this was the equation, and we find that this is the, if this is the equation, then it is the solution. So, here we will going to get a plane wave solution, and this plane wave solution of the Maxwell's wave equation is of the form like E is equal to E0 e to the power of I k dot r minus omega t. That is the solution when k is equal to omega divided by c. So, under this condition, you can, if you plug this solution here, plug this expression E to this equation here, you will going to see that this is basically the solution of that. So, we can check it quickly. So, what is grad square E? Because I need to first calculate this quantity. So, this is, if I do that in Cartesian coordinate, so it is d2x plus d2y plus d2z, and it should be operated on E, and E is E0, I should put a vector here, vector, then exponential I, and here we have kxx plus kyy plus kzz. I just expand the k vector. So, my k vector here is kx unit vector x plus ky unit vector y plus kz unit vector z, and my r is x unit vector, y unit vector, and z unit vector z. So, then minus of omega t bracket close, and if I operate these things, then what we get is this one. So, this will going to operate twice, and every time it operates, so I k will come out. In this case, when we operate over operated by del y, so it I k y will come out and so on. So, eventually we have this, we have k x square plus k y square plus k z square, and rest of the term will remain same. So, I just simply write my is E 0 e to the power of I k dot r minus omega t. So, this is simply minus of k square E. What about the right hand side? This is the left hand side. What about the right hand side? The right hand side I can write here. The right hand side is 1 by c square d2 dt square. So, if I write 1 by c square d2 e dt square, so it should be simply minus of omega square c square and this e, and we already mentioned that k should be equal to omega by c, for which the solution is there. So, we can see that the left hand side is equal to right hand side. So, that means this is a solution. This is a solution for Maxwell's wave equation, and we are going to use this solution. This is a special property. Why we call a plane wave, we will may discuss in the next class. So, I do not have much time today to discuss further. So, I would like to stop here. So, in the next class, maybe we will going to find out more about the solution and the relative direction between the E and B, because B will also follow the same equation. So, the solution of the B will also be a plane wave solution, and then we will discuss that how to find out the relative direction of E, B, the value etc., by just exploiting the Maxwell's other equation, which is the Gauss's law and others law. So, with that note I would like to conclude. Thank you for your attention and see you in the next class.